Welcome everyone. Today in this presentation, we'll learn about the plate tectonics. Plate tectonics is a scientific theory describing the large-scale motion of the seven plates and movement of larger number of smaller plates of the Earth's lithosphere. Since tectonic processes began on the Earth between 3.3 to 3.5 billion years ago, this model builds on the concept of continental drift, an idea that developed during the first decade of the 20th century. The geoscientific community accepted plate tectonic theory after floor spreading was validated in late 1950s and in early 1960s. The lithosphere, which is the outermost ridged part of the planet, is broken into different plates which are known as tectonic plates. The Earth's lithosphere is composed of seven major plates and many minor plates. There are some microplates as well. Where the plate meets, their relative motion determines the type of boundary, that is convergent boundary, divergent boundary, or transform boundary. There are intermediate nature of boundaries as well. The earthquake, volcanic activity, mountain building, and oceanic trench formation, these all occur along these plate boundaries. The relative movement of plate typically ranges from 0 to 100 millimeter annually. Tectonic plates are composed of oceanic lithosphere, which are somewhat thinner, and thicker continental lithosphere, which are topped by its own kind of crust. Along the convergent boundaries, subduction, or one plate moving another under, carries lower one into the mantle and material is lost, that is roughly balanced by formation of new oceanic crust along divergent plate boundaries by seafloor spreading. In this way, the total surface of the lithosphere remains constant. This prediction of plate tectonics is also referred as conveyor belt principle. Earlier theories, since they are disproven, propose the gradual sinking or contraction or gradual expansion of the globe. The tectonic plates are able to move because Earth's lithosphere has greater mechanical strength than underlying asthenosphere. Lateral density variation in the mantle results in convection, that is, the slow creeping motion of the Earth's solid mantle. Plate movement is thought to be driven by a combination of motion in the seafloor away from the spreading ridge due to variation in topography, density changes in the crust. At subduction zone, the relatively cold dense oceanic crust is pulled or sink down into the mantle over the downward convecting climb of mantle convection cell. The idea that continents, particularly South America and Africa, fit together like pieces of a jigsaw puzzle came about during the 1600s as better world map became available. However, little significance was given to this notion until 1915 when Alfred Wegener, a German meteorologist and geophysicist, wrote The Origin of Continents and Ocean. This book outlined the Wegener's hypothesis called a continental drift, which dared to challenge the long assumed that continents and ocean basins have been fixed at their geographic positions. This is the paper which outlines the concept of continental drift and gives evidences of the continental drift. Although today we know that there is nothing like continental drift, rather than these are lithospheric plates which are moving in relation to each other. Either they are going away from each other, so we have divergent boundaries, or they are coming towards each other, so we have convergent boundaries, or they are sliding past each other, so we have transform boundaries. Apart from those, we have some boundaries which are intermediate in nature, that are transpressional and transtensional boundaries. So Wagner suggested that a single supercontinent consisting of all Earth's landmass once existed, and he named this giant landmass Pangaea. Wagner further hypothesized that about 200 million years ago, during the early part of Mesozoic era, this supercontinent began to fragment into smaller land masses. These continental blocks then drifted to their present positions over the span of millions of years. So we can see over here we have Pangaea, and it is surrounded by a single ocean, that is Tethys Ocean, and that was in fact the Panthalassa. When Pangaea was broken into this Gondwana and Laurasia, then we have Tethys Ocean in between. The Wagner and others who advocated the continental drift hypothesis collected substantial evidences to support their point of view. The fit of South America and Africa and the geographic distribution of fossils and ancient climates, these all seem to buttress the idea that these now separated land masses were once joined. So this is what the Pangaea looked like before 250 million years ago. And we have overlapped the political boundaries of today's condition. So if we overlap the political boundary of today, this is how the Pangaea must have been looked like, and what must have been the position of countries in relation to each other. In order to prove his idea of movement of the continents, Wagner had to give certain evidences. These evidences includes the continental jigsaw puzzle, fossil matching across the seas, rock types and geological features, ancient climates or paleoglaciation evidences, and also the evidences regarding the paleomagnetism. So let's see these evidences one by one. The evidence of continental puzzle. So like few others before him, the Wagner suspected that continents might once have been joined when he noticed the remarkable similarity between the coastline of opposite sides of the Atlantic Ocean, as we can see here in the diagram. However, the Earth scientists challenged the Wagner's use of present-day shoreline to fit these continents together. These opponents correctly argued that wave erosion and depositional processes continuously modifying the shorelines. Even if the continental displacement had taken place, a good fit today would be unlikely. Because Wagner's original jigsaw fit of the continents was crude, it is assumed that he was aware of this problem. Scientists later determined the much better approximation of the outer boundary of a continent is seaward edge of continental shelf, which is lying submerged a few hundred meters below the sea level. In early 1960s, Sir Edward Bullard and two associates of him constructed a map that pieced together the edge of continental shelves of South America and Africa at a depth of about 900 meters. The remarkable fit obtained was more precise than even these researchers has expected. So we can see here, after the blue boundaries, we have the real continental boundaries. If we are going to fit these boundaries rather than the shorelines, it is much more appropriate fit, more than 90 to 95% fit. So the idea of the continental drift arose from this coastline similarity, and today we have been able to make this fit even more than 90% when we are matching the continental shelf lines rather than the shorelines. The second evidence Wagner gave was fossil matching across the seas, which are now available on the continental landmass, which are separated by huge ocean in between. The identical fossil organisms, for example, Mesosaurus and Glossopteris, as we can see here in the diagram. The Mesosaurus is a fossil reptile and Glossopteris is a flora. So they had been discovered in the rocks from both South America and Africa, which are now separated from each other by a huge ocean, Atlantic Ocean in between. The most paleontologists agreed that some type of land connection was needed to explain the existence of similar Mesozoic age life forms on widely separated land masses. Just as modern land life forms native to North America are not the same as those of Africa and Australia during the Mesozoic era, organisms on widely separated continents should have been distinctly different. Mesosaurus is a small aquatic freshwater reptile whose fossil remains are limited to black shells of Permian period, roughly about 260 million years, in eastern South America and southwestern Africa. If the Mesosaurus had been able to make long journey across the South Atlantic, its remains should be more widely distributed. As this is not the case, the Wagner asserted that South America and Africa must have been joined during the period of Earth's history. So how did the opponents of continental drift explain the existence of identical fossil organisms in the places separated by thousands of kilometers of open ocean? The rafting, as we can see here in the diagram. So organisms rafted and went from one continent to another, highly unlikely. Transoceanic ridges and land bridges like Eskimo links and island stepping stone that were most widely invoked explanation of those migrations. We know, for example, that during ice age that extended about 8,000 years ago, the lowering of sea level allowed mammals, including humans, to cross the narrow Bering Strait that separates Russia and Alaska. Was it possible that land bridges once connected the Africa and South America but later subsided below the sea level? The modern maps of the seafloor substantiates the Wagner's connection that if land bridges of this magnitude existed, their remains would still lie below the sea level. Another evidence which Wagner gave was rock types and geological features. So if a continents were together, the rocks found in a particular region on one continent should closely match in age and type those found in ancient positions on the adjoining continents. Wagner found evidences of highly deformed igneous rocks in Brazil that closely resembled similar rocks in Africa. Now they are separated. Similar evidences can be found in mountain belts that terminates at one coastline and appear on landmass across the ocean. For instance, the mountain belt that includes Appalachian trends northwestward through the eastern United States and disappeared off the coast of Newfoundland, as we can see here in the figure. The mountain of comparable ages and structures are found in the British Isles of Scandinavia. When these land masses are positioned as they were about 200 million years ago, as it has been shown in the figure, the mountain chains form a nearly a continuous belt. Because Alfred Wegener was a student of world climate, he also gave the idea of ancient climates for the supplementation of his continental drift theory. He suspected that paleoclimatic data might also support the idea of mobile continents. His assertion was bolstered by evidences that glacial periods during the late Paleozoic had been discovered in southern Africa, South America, Australia, and in India. This meant that about 300 million years ago, the vast ice sheet covered extensive portions of southern hemisphere as well as India. Much of the land area that contains evidence of Paleozoic glaciation presently lies within 30 degrees of equator in subtropical and tropical climates. How could extensive ice sheets form near equator? One proposal suggests that our planet experienced period of extreme global cooling. The Wagner rejected this explanation because during the same span of geologic time, large tropical swamps existed in several locations in northern hemisphere. The lush vegetation in these swamps was eventually buried and converted into the coal. Today, these deposits comprise major coal fields in the eastern United States and northern Europe. Most of the fossils found in these coal-bearing rocks were produced by trees, ferns with large fronds, a fact consistent with warm moist climate. The existence of these large tropical swamps, Wagner argued, was inconsistent with the proposal that extreme global cooling caused glaciers to form in areas that are currently tropical. Wagner suggested a more plausible explanation for the late Paleozoic glaciation, that the supercontinent Pangaea was having. The southern continents being joined together and located near the South Pole would account for polar conditions necessary to generate extensive expanses of glacial ice over much of these land masses. At the same time, this geography places today's northern continents near the equator and accounts for tropical swamps that generated the vast coal deposits. How does a glacier develop in hot, arid Central Australia? How do land animals migrate across wide expanses of the ocean? As compelling as this evidence may have been, 50 years passed before most of the scientific community accepted the concept of continental drift and the logical conclusions to which it led. The next evidence that Wagner gave was paleomagnetism. So, although the Alfred Wagner would not live to see it, his theory of plate tectonics would gradually gain acceptance within the scientific community as more evidences began to accumulate. Some of the most important evidence came from the study of paleomagnetism, or changes in the Earth's magnetic field over millions of years. The Earth's magnetic field is defined by north and south poles that align generally with the axis of rotation. It is roughly different from the axis of rotation, currently roughly 11.2 degree. The lines of magnetic force flow into Earth in the northern hemisphere and out of the Earth from the southern hemisphere. Because of the shape of the field lines, the magnetic force tends at different angles to the surface in different locations. At the north and south poles, the force is vertical. Anywhere on the equator, the force is horizontal, and everywhere in between the magnetic force is at some intermediate angle to the surface. In fluid form, the minerals that make up magma are free to move in any direction and take on any orientation. But as the magma cools and solidifies, the movement ceases and the mineral orientation and position becomes fixed. As the mineral magnetite Fe3O4 crystallizes from the magma, it becomes magnetized with the orientation parallel to the Earth's magnetic field at that time, similar to the way a compass needle aligns with the magnetic field to point north. This magnetic record in the rock is called remnant magnetization. The rocks like basalt, which cool from a high temperature and commonly have relatively high levels of magnetite, are particularly susceptible to being magnetized in this way. But even sediments and sedimentary rocks, as long as they have small amounts of magnetite, will take on remnant magnetization because the magnetite grains gradually becomes reorientated following the deposition. By studying both the horizontal and vertical component of remnant magnetization, one can tell not only the direction of magnetic north at the time of rock's formation, but also the latitude where the rock formed relative to the magnetic north. This figure depicts the orientation of magnetic north and south in normal polarity condition. The first figure represents the orientation of magnetic north and south in normal polarity conditions. So this is north and this is south, and this represents in reverse polarity condition, and in between these are the time of reversal, which are shown by this particular diagram. In early 1950s, a group of geologists from Cambridge University started looking at remnant magnetism of Phanerozoic, British and European volcanic rocks and started collecting paleomagnetic data. They found that rocks of different ages sampled from generally the same area showed quite different apparent magnetic pole positions. They initially assumed that this meant that Earth's magnetic field had over time departed significantly from its present position, which is close to the rotational pole. The curve defined by paleomagnetic data was called polar wandering path. We now know that the magnetic data define movements of continents and not of magnetic poles, so we call it an apparent polar wandering path, or APWP. Following the World War II, oceanographers equipped with new marine tools and ample of funding from US Office of Naval Research embarked on an unprecedented period of oceanographic exploration. Over the next 2 decades, a much better picture of large expanses of seafloor slowly and painstakingly began to emerge. From this work came the discovery of a global oceanic ridge system that winds through all major plates. In the other parts of the ocean, new discoveries were being made. Studies conducted in the Western Pacific demonstrated that earthquakes were occurring at great depths beneath deep oceanic trenches. Of equal importance was the fact that dredging of the seafloor did not bring up any oceanic crust that was older than
180 million years. Further, sediments accumulation in the deep ocean basin were found to be thin and not thousands of meters that were predicted earlier. By 1968, these developments, among others, had led to unfolding of a far more encompassing theory than continental drift, and this theory is known as plate tectonic theory or theory of plate tectonics.
From the deepest ocean trench to the tallest mountain, plate tectonics explain the features and movement of the Earth's surface in the present and the past. Plate tectonics is the theory of Earth's outer shell that is divided into several plates that glide over the mantle. The plate acts like hard and rigid shell compared to the Earth's mantle. This strong outer layer is called lithosphere, which is roughly 100 kilometers thick. The lithosphere includes crust and outer part of the mantle. Below the lithosphere, there is a asthenosphere, which is malleable or partially malleable, allowing the lithosphere to move around. It is how our plates move above the asthenosphere.
According to the plate tectonics model, the crust and the uppermost and therefore the coolest part of the mantle constitutes the Earth's strong outer layer, the lithosphere. The lithosphere varies in both thickness and density depending on whether it is oceanic or continental lithosphere. Oceanic lithosphere is roughly 100 kilometers, that is 60 miles thick in deep ocean basins, but it is considerably thinner along the crest of oceanic ridge systems. By contrast, as we can see in this diagram, the continental lithosphere averages about 150 kilometers, that is 90 miles thick, but may extend up to depth of 200 kilometers or more beneath the stable interior of the continents. Further, the composition of both oceanic and continental crust affects their relative densities. The oceanic crust is mainly composed of basaltic rocks, whereas the average composition of continental crust is granite to granodiorite. So here we can see the oceanic lithosphere, which is subducting, and continental lithosphere, which is overriding. So oceanic crust is composed of basalt that is rich in dense iron and magnesium, whereas the continental crust is composed largely of less dense granitic rocks. Because of these differences, the overall density of oceanic lithosphere, the crust and upper mantle, is greater than that overall density of continental lithosphere. The asthenosphere is a weak, hotter region in the mantle that lies below the lithosphere. The temperature and pressures in the upper asthenosphere, that is 100 to 200 kilometers in depth, they are such that the rocks at this depth are very near to their melting temperatures and hence respond to the forces by flowing similar to the way a thick liquid would flow. By contrast, a relatively cool and rigid lithosphere tends to respond to forces acting on it by bending or breaking, but not by flowing. Because of these differences, Earth's rigid outer shell is effectively detached from the asthenosphere, which allows these layers to move independently and create plate tectonics. So, how many major plates are there? The lithosphere is broken into about dozen of segments of irregular sizes and shapes. They are called lithospheric plates or simply plates. that are in constant motion with respect to each other. 7 major lithospheric plates are recognized and account for 94% of the Earth's surface area. The North American plate, the South American plate, Pacific plate, African plate, Eurasian plate, Indo-Australian plate, and Antarctic plate. The largest is Pacific plate, which encompasses a significant portion of Pacific basin. Each of the 6 other large plates consists of entire continent as well as significant amount of oceanic crust. Notice that in South American plate encompasses almost of all America and about 1/2 of the floor of South Atlantic Ocean. Note also that none of these plates are defined entirely by a margin of single continents. This is a major departure from Wagner's continental drift hypothesis, which proposed that continents moved through the ocean floors and not with it. So together with the major plates, we have some intermediate size plates that includes Caribbean, Nazca, Philippine, Arabian plate, Cocos plate, Scotia plate, and Juan-Fuca plates. These plates, with the exception of Arabian plates, they are composed mostly of oceanic lithosphere. Plate movement. One of the main tenets of the plate tectonic theory is that the plate moves as somewhat rigid unit relative to each other. As the plates move, the distance between two locations on the different plates, such as New York and London, gradually changes, whereas the distance between the sites on the same plates, for example New York and Denver, they remains relatively constant. However, a part of some plates are comparatively weak and can become fragmented. So here we can see the ternary diagram of the plate movement, in which we have pure components of movement along the edges of this triangle, like divergent movement when the plate is purely moving away from each other. Then we have convergent movement, in which the one plate is moving towards another plate. So if one is oceanic and another is continental, oceanic being denser will subduct beneath the continental one, or if both the plates will be of oceanic nature, the older oceanic lithosphere is going to subduct below the younger oceanic lithosphere. And in case if both the plates are continental in nature, they are going to collide and create the largest orogenies. And we have third type of plate movement, which is known as strike slip movement, in which one plate moves past another plate. So here at divergent plate boundaries, we have creation of new lithosphere. So this is also known as constructive plate boundary, and at convergent boundary we have destruction of the crust. So this is known as destructive plate boundary, and here theoretically we do not have any construction or destruction of the crust. So this is known as conservative plate boundary. Apart from that, we have some intermediate plate movements as well, where the divergence and strike slip movements are going together. This type of movement will be known as transtension. And if the divergent and strike slip and compression will go hand in hand, these type of movements will be transpression. And if the convergence and divergence occurs together along some plate boundaries, this is syn convergence extension type of movement. So now let's classify the plate boundaries. So here we can see in the diagram we have divergent plate boundaries, where two plates move apart from each other, as represented by these red lines. Convergent plate boundary, where two plates move together, resulting either in oceanic lithosphere descending beneath the overriding plate, eventually to be reabsorbed into the mantle, or possibly in the collision of two continental blocks to create a mountain belt. So convergent boundaries are indicated by blue lines in this diagram, we can see here. And then we have transform plate boundaries, where two plates grind past each other without the production or destruction of lithosphere. The divergent and convergent plate boundaries each account for about 40% of all plate boundaries. So transform boundaries or faults accounts for remaining 20%. So we can see over here that these are the boundaries: convergent, divergent, and transform. The divergent boundaries and transform boundaries, they are associated with each other. In fact, all the boundaries are associated with each other. No boundary can occur in isolation, because in order to move a plate, there should be movement relative to another plate. In order to understand the concept of seafloor spreading, we must first understand some basic concepts that from the cornerstones for concept of seafloor spreading. These cornerstones are conventional current theory and paleomagnetism. So now let's study the conventional current hypothesis by Arthur Holmes. Arthur Holmes postulated convection current theory in year 1928 and 29. It was widely accepted driving mechanism for continental drift, which led to the foundation of modern plate tectonics. According to Holmes, the main source of convection current is molten mantle, where disintegration of radioactive material generate heats regularly. The convective currents depends upon two factors. First, on the thickness of crust near the equator and poles, and second, on uneven distribution of radioactive elements. There are two situations of rising convective currents when they reach the lower limit of crustal masses. The first one, the crustal mass where two rising convective currents diverge in opposing directions, is stretched and thinned into tensional forces, and ultimately the convective currents are divided into two groups on the basis of their location aspects. For example, the convective currents of rising columns and convective currents of falling columns. So these are rising columns and these are falling columns. The rising convective currents, after reaching to the lower limit of the crust, diverge. Now let's study all type of plate boundaries one by one. So first we are going to take the divergent plate boundaries and seafloor spreading. The majority, but not all, divergent plate boundaries are associated with oceanic ridges. Oceanic ridges are elevated areas of the seafloor that are characterized by the mechanism that operates along oceanic ridge system to create new seafloor is appropriately called seafloor spreading. Spreading typically averages around 5 cm per year, roughly the same rate at which a human fingernail grows. This diagram represents that how the mid-oceanic ridges are formed and how the seafloor spreading occurs. So in first portion or in first phase, there is generation of faulting because of the hitting of magma from below. So whenever you have generation of fault lockups, gradually because of divergence, these particular. In the early 1960s, Princeton's geologist Harry Hess proposed the hypothesis of seafloor spreading, in which the basaltic magma from the mantle rises to create a new oceanic floor at mid-oceanic ridges. On the each side of ridge, the sea floor moves from a ridge. So the paleomagnetism is a study of record of magnetic field with the help of magnetic field recorded in the rocks and sediments or in archaeological materials. The polarity of Earth's field and magnetic field reversals are thus detected by studying the rocks of different ages. The rocks formed from underwater. So these oceanic ridges are the boundaries where tectonic plates are diverging or moving apart. The fissure or vent in between the ridge between the plates allowed the magma to rise and harden into a narrow band of rocks on either side of the vent. We can see in this diagram as well, as the magma rises, it spreads across the ridges and forms the new oceanic crust. So whenever you have normal polarity condition, for example, for now we are in normal polarity condition, so the rocks which are being created this time, they are being locked in normal polarity directions. Comparatively, slow spreading rates of 2 cm a year is found along the mid-Atlantic ridge, whereas spreading rate exceeds 15 centimeters per year that have been measured along the sections of East Pacific rise. Although, now let's watch a video about the seafloor spreading and plate tectonic evidence. The link of the video is given in this slide. Another type of structure at diverging plate boundaries are continental rifts. So continental rifts are fault bounded valleys that ranges in width from 30 to 75 kilometers and in length from tens to hundreds of kilometers. They are characterized by tension. So the divergent plate boundaries can develop within a continent, in which case the landmass may split into two or more smaller segments separated by an ocean basin. Continental rifting begins when a plate motion produces tensional forces that pull and stretch the lithosphere. The longest modern rift system is the East African system, which extends more than 6,500 kilometers from the western part of Asia Minor to southeastern Africa. The Basin and Range Province in western North America is a multiple rift system composed of a complex series of alternating gravens. Convergent plate boundaries and subduction. Actually, the new lithosphere is constantly being produced at oceanic ridges we have already studied. However, our planet is not growing larger. Its total surface area remains constant. So a balance is maintained because of older, denser portion of oceanic lithosphere descends into the mantle at a rate equal to the seafloor spreading, as we can see in this particular diagram that the oceanic lithosphere is going below the mantle. This activity occurs along convergent plate boundaries where two plates moves towards each other. So this one is moving towards this and this one is towards this. Similarly, we can see in these plates, similarly, these are two plates which are moving towards each other. So the leading edge of one plate is bent downward as it slides beneath another plate. The convergent boundary is also called subduction zone because they are the sites where lithosphere is descending, being subducted into the mantle. Subduction occurs because the density of the descending lithosphere plate is greater than the density of the underlying asthenosphere. So if we see the asthenosphere, the density of this plate is more than the density of asthenosphere. In general, old oceanic lithosphere is about 2% more dense than the underlying asthenosphere, which causes it to subduct. The continental lithosphere, in contrast, is less dense than the underlying asthenosphere and resists subduction. As a consequence, only oceanic lithosphere will subduct to great depths. Deep oceanic trenches are the surface manifestations produced as the oceanic lithosphere descends into the mantle. These large linear depressions are remarkably long and deep. The Peru-Chile Trench along the west coast of South America is more than 4,500 kilometers long, and its floor is as much as 8 kilometers below the sea level. The Western Pacific trenches, including Mariana and Tonga trenches, tend to even deeper than these trenches of Eastern Pacific. So, Western Pacific contains the most deepest trenches of the world. For example, this trench is Mariana Trench. This is situated in Western Pacific, and the deepest point in Mariana Trench is known as Challenger Deep. This is roughly 13 kilometer deep. So what defines the depth of the trenches is in fact the angle of subduction, and that is in turn defined by the age of oceanic lithosphere, which is being subducted below another oceanic lithosphere. The slabs of oceanic lithosphere descends into the mantle at an angle that vary from few degree to nearly vertical, that is roughly 90 degree. The angle at which oceanic lithosphere subducts depends largely on its age, therefore on its density. For example, when sea floor spreading occurs near the subduction zone, as is the case along the coast of Chile, the subducting lithosphere is young and buoyant, which results in a low angle descent. As two plates converge, the overriding plate scraps over the top of subducting plate below. A type of forced subduction is now encountered. Consequently, the region around Peru-Chile Trench experiences great earthquake, including the 2010 Chilean earthquake, one of the top 10 on the record. As the oceanic lithosphere ages, that is, it gets farther from the mid-oceanic ridges or spreading centers, it gradually cools, which causes it to thicken and increase in its density. In parts of the Western Pacific, some oceanic lithosphere is 180 million years old, the thickest and densest in the today's ocean, for example, along the Mariana Trench. The very dense slabs in this region typically plunges into the mantle at angles approaching 90 degrees. This is largely explains why most trenches in the Western Pacific are deeper than the trenches in the Eastern Pacific. So as we can see in this diagram that there are a different subduction angle for the oceanic lithosphere. So this is the oceanic lithosphere, this is subducting along active margin. We can see that this is subducting just near to the divergent plate boundary. So divergent is somewhat near, so its age is somewhat less. So this is subduction is rather a forced subduction and low angle subduction. So lots of scrapping of the material takes place along the subduction zone, so it results in great earthquakes. As we are going down in this diagram B and C, we can see that the aging of the lithosphere is taking place, the thickness of oceanic lithosphere is increasing, so the subduction angle becomes more and more, and here the angle is roughly equals to 90 degree, for example in case of Mariana Trench. So here we have this steep subduction because of greater age of oceanic lithosphere and also the greater density of oceanic lithosphere. So we have the deepest trenches along the zones where we have this steep angle subduction, and steep angle subduction occurs only when we have some aged oceanic lithosphere. This diagram after Hosong and Fryer 1981 explains the schematic cross section sketch of Mariana Arc. So here we can see that this oceanic lithosphere which is being subducted over here is very old. It is roughly 180 million year in age, and its density is very fast. As we can see, the seismic waves are traveling with a faster velocity that shows its density and compactness of the plate. So this results in a steep angle subduction. So if the steep angle subduction occurs, we have now the ease in subduction because of denser oceanic plate. So this plate easily gets subducted. The gravity pull helps this plate to get subducted into the mantle. So we get the deepest trenches along these zones, and these zones lies along the western Pacific region. Again, this diagram explains the arc-tench gap. That explanation is based on angle of subduction. If we have angle of subduction that is gentler, so the subducting plate, in order to reach the greater depth, it has to travel some more distance. So if it has to reach 3 kilometers with gentle angles, it will have to travel more and more distance to reach 3 kilometer vertical depth. So when it reaches 300 kilometer or more, the plate gets melted along the Benioff zone, and this molten lava assimilates to the upper riding plate, and we have formation of arcs. And here along the subduction we have development of trenches. As we can see here, along the subduction zone the trench develops, and when the plate reaches to the greater depth, that is Benioff zone, it melts, and so that particular lava assimilates with the upper riding plate and produces the chain of volcanoes that is defined as arc. So if the angle is gentle, this distance between the trench and arc is more, and if the subduction angle is steep, that is if this subduction is occurring at 90 degree or near to 90 degree, what is happening, this plate is reaching to the greater depth by only traveling a very small horizontal distance. So it is going to achieve this depth of melting at traveling very small horizontal distances, so arc trench gap will be narrow. Although all convergent zones have the same basic characteristic, they vary considerably depending on the type of crustal material involved and the tectonic settings as well. The convergent boundaries can form between the oceanic plate and one continental plate, as we can see over here, between two oceanic plate, as we can see in this diagram, or between two plates, one involves the continent, another also involves the continents. So it can also occur between two continental plates. As we can see all these three settings in this particular diagram: the convergence between continent and ocean, the convergence between ocean and ocean, and the convergence between continent and continent. Let's explain these settings one by one. So now let's study the first type of convergence, that is oceanic-continental convergence. So when the leading edge of a plate capped with a continental crust converges with a slab of oceanic lithosphere, the buoyant continental rock remains floating while the denser oceanic slab sinks into the mantle. When a descending oceanic slab reaches at a depth of about 100 kilometers, that is 60 miles, the melting is triggered within the wedge of hot asthenosphere that lies above it. But how does the subduction of a cool slab of oceanic lithosphere cause mantle rock to melt? The answer lies in the fact that water contained in the descending plates act the way salt does to the melting ice. that is, the wet rock in high pressure environment melts at substantially lower temperature than the dry rock do in the same condition. So when this plate subducts, this carries some hydrated minerals and also some water together with it. So when it reaches to the greater depth, this hydration or water makes the wet conditions for this plate that lowers its melting point at high pressure conditions. So we have melting of this subducting lithosphere along these zones. So this depth varies roughly from 100 to 300 kilometer. So because the lithosphere itself is roughly 150 kilometer to 200 kilometer from the surface, which zone lies at 300 kilometer, or we can say when it subducts more 100 kilometers, then we have encounter of Benioff zone. So the melting of this plate takes place, and this leads to formation of magma and also the partial metal melting. So this magma assimilates with the overriding plates, and there is formation of the volcanic chain, as we can see over here. When the oceanic plate descends into the asthenosphere, the water is driven from the subducting slab that lowers the melting temperature of rock that is sufficiently enough to generate magma. So this is cascade range of volcanism. This is formed by the subduction of Juan de Fuca plate. So this is Juan de Fuca plate under the North American plate. So we can see that Juan de Fuca plate is subducting under North American plate, and number of volcanoes are being formed at overriding North American plate. The volcanoes of towering Andes are the product of molten rock generated by the subduction along the Nazca plate beneath the South American continent. As we can see, this is South American continent, and the Nazca plate is subducting below this continental lithosphere. The mountain system like Andes, which are produced in part by volcanic activity associated with the subduction of oceanic lithosphere, they are called continental volcanic arc. So these are Andes mountains. In fact, they are continental volcanic arc. As we can see that along the Pacific zone, here the Nazca plate is subducting along the South America over here. So after the melting of this subducted plate, the molten magma assimilates with the overriding plate, and there is production of chain of volcanoes. This is in fact a continental volcanic arc, because this overriding plate is continental plate. The Cascade Ranges in the Washington, Oregon and California is another mountain system consisting of several well-known volcanoes, including the Mount Rainier, Mount Shasta, St. Helens and Mount Hood, as we have seen in the earlier figure. The active volcanic arc also extends into the Canada, where it includes Mount Gibraldi and Mount Silver Throne. So let's study now the second type of convergence, that is oceanic convergence. Here the one older oceanic lithosphere subducts below the younger oceanic lithosphere. An oceanic convergent boundary has many features in common with oceanic continental margin, where the two oceanic slabs converge, one descends beneath the another, initiating volcanic activity by the same mechanism that operates at all subduction zones. Water driven from the subducting slab of oceanic lithosphere triggers the melting in the hot wedge of mantle rock above. In this setting, the volcanoes grows up from the ocean floor rather than on a continental platform. As we can see over here, that here the oceanic lithosphere is subducting below another oceanic lithosphere. So when it reaches to the greater depth where the melting can occur, now This produces a chain of volcanoes on overriding oceanic plate. When subduction is sustained, it will eventually build a chain of volcanic structures large enough to emerge as islands. The newly formed land consisting of arc-shaped chain of volcanic island is called volcanic island arc or simply island arcs. The Aleutian, Mariana and Tonga Island are examples of relatively young volcanic island arc. Island arcs are generally located 120 to 360 km from the deep oceanic trenches. Located adjacent to the island arc just mentioned are Aleutian Trench and Mariana Trench and the Tonga Trench. So what varies this distance between the arc and trench is in fact the angle of subduction. If the younger oceanic lithosphere is subducting below another oceanic lithosphere which is relatively more younger, so angle of subduction is going to be gentle and the arc trench gap will be more and more. If the relatively older oceanic lithosphere, for example of 180 million year old, is going to subduct below another oceanic lithosphere, so because of the aging, the oceanic lithosphere achieves the thickness as well as density. This facilitates the steeper angle subduction. So by traveling the less horizontal distance, it travels the more vertical distance and reaches to the depth at which the melting can take place. And now the arc trench gap is relatively less. Most volcanic islands are located in the Western Pacific. Only two are located in Atlantic. The Lesser Atlantic arc on the eastern margin of Caribbean Sea and the Sandwich Island located at the tip of South America. The Lesser Antilles are the product of subduction of Atlantic Ocean floor beneath Caribbean plate. Located within this volcanic arc are Virgin Islands of the United States and Britain as well as the island of Martinique, where the Mount Pelee erupted in 1902, destroying the town of Saint Pierre and killing an estimated of 28,000 people. This chain of islands also includes Mount Sarret, where the volcanic activity has occurred as recently as in 2010. The island arcs are typically simple structures made up of numerous volcanic cones underlain by oceanic crust that is generally less than 20 kilometers, that is 12 miles thick. By contrast, some island arcs are more complex and are underlain by highly deformed crust that may reach 35 kilometers in thickness. These examples include Japan, Indonesia and Alaskan Peninsula. These island arcs are built on material generated by earlier episode of subduction on the small silvers of continental crust that have rafted away from the mainland. So these examples include the volcanoes of the Aleutian Island. The Aleutian Island are volcanic island arc produced by subduction of the Pacific plate beneath the North American plate. So here we can see the number of active volcanoes. The third type of convergent boundary results when one landmass moves towards the margin of another because of subduction of intervening seafloor, where the oceanic lithosphere tend to be dense and sink into the mantle. The buoyancy of continental material inhibits it from being subducted. Consequently, a collision between two converging continental fragments ensues. This event folds and deforms the accumulation of sediments and sedimentary rocks along the continental margin as if they had been placed in the gigantic voice. The result is the formation of new mountain belt composed of deformed sedimentary and metamorphic rocks that often contains silvers of oceanic lithosphere. So here we can see the such a collision and also the effect of such a collision. This is the peak highest in the world, that is, this peak is Mount Everest. So such collision began about 50 to 55 million years ago when the subcontinent of India rammed into the Asia, producing the Himalayas, the most spectacular mountain ranges on earth. During this collision, the continental crust buckled and fractured and was generally shortened horizontally and thickened vertically. In addition to the Himalayas, several other mountain systems including Alps, Appalachians and Urals formed as the continental fragments collided to another continental lithosphere. After the convergent boundary, that is destructive boundary, we have divergent boundary, that is constructive boundary. The convergent is destructive because along that we have destruction of the crust, and along the divergent boundaries we have creation of new oceanic lithosphere. So this is known as constructive boundary. We have a third type of boundary which is known as transform plate boundary. This transform plate boundary, that is also known as transform plate, the plate slides horizontally past each other without the production and destruction of the lithosphere theoretically. The nature of transform faults was discovered in 1965 by Canadian geologist J. Tuzo Wilson, who proposed that these are large faults connecting two spreading centers. So these are two spreading centers, that is divergent boundaries, or less commonly two trenches, that is convergent plate boundaries. Most transform faults are found on the ocean floor where they offset the segments of oceanic ridge system, producing a step-like margin, as we can see over here. Notice that the zigzag shape of mid-Atlantic ridge in roughly reflects the shape of virginal rifting that caused the breakup of the supercontinent Pangaea, compared to the shape of continental margins of the landmass on both the side of Atlantic and the shape of mid-Atlantic ridge. So they have got similarity. So here we can see that two mid-oceanic ridges are separated by transform faults. So these are in fact transform plate boundaries. If we see all this zone, this is a transcurrent fault in which where the relative movement is past each other, this is transform zone. Most of the earthquake activities and volcanism occurs along this zone. This is the active zone, and because the plate movement is in the same direction along these zones, these are inactive zones. Typically, the transform faults are part of prominent linear breaks in the seafloor known as fracture zones, which includes both the active transform fault and their inactive extension into the plate interior. The active transform faults lie only between two offset ridge segments and are generally defined by big shallow earthquakes. Here the seafloor produced at one ridge axis moves in opposite directions of seafloor produced at an opposing ridge segment. Thus, between the ridge segments, these adjacent slabs of oceanic crust are grinding past each other along the transform fault. Beyond the ridge crest are inactive zones where the fractures are preserved as linear topographic depression, and the trend of these fracture zones roughly parallels the direction of the plate motion at the time of their formation. Thus, these structures help geologists to map the direction of plate motion in the geological past. Here we can see a transform fault along the continental margin. Here we can see this is a San Andreas fault which is transform in nature. Here the Pacific plate is moving in southwest direction roughly, and the North American plate is moving roughly in northeast direction. So this produces overall a strike slip movement between the North American plate and Pacific plate, and this is facilitated by different plates like Juan de Fuca plate, which is subducting and producing the Cascadian ranges. And here this movement is facilitated by yet another fault, which is Mondaquino transform fault. So we have occurrence of number of earthquakes because of the movement of these two plates along the Los Angeles, San Francisco, etc. The transform faults also provide the means by which the oceans or oceanic crust created at the ridge crest can be transported to the site of the destruction, that is at the deep oceanic trenches. Notice that the Juan de Fuca plate moves in the southeasterly direction, as we have seen in the previous slide, eventually being subducted under the western coast of the United States and the Canada. The southern end of the plate margin is bounded by transform fault that is known as Mondaquino fault. This transform boundary connects the Juan de Fuca ridge to the Cascadian subduction zone. Therefore, it facilitates the movement of the crustal material created at the Juan de Fuca ridge to the destruction zone beneath the North American continents. Like the Mondaquino fault, most of the transform fault boundaries are located within the ocean basin. However, few cut through continental crust. Two examples are the earthquake prone San Andreas fault of California and New Zealand's Alpine fault. We can notice in this figure that the San Andreas fault connects spreading centers located in the Gulf of California to the Cascadian subduction zone and to the Mondaquino fault. Along the San Andreas fault, the Pacific plate is moving towards the northwest past the North American plate. If the movement continues, the part of California west of the fault zone, including Mexico, Baja Peninsula, will become an inland off the west coast of United States, Canada. However, the more immediate concern is the earthquake activity triggered by the movement along this fault system. The movement along the San Andreas fault, this aerial view shows the offset in the dry channels of Wallace Creek near Taft, California. So because of this transform movement, there has been offset in this creek. So here is a Wallace Creek. This movement has taken place because of the activity along the transform San Andreas fault. So what are the drivers that operate our lithospheric plates? So researchers are in a general agreement that some type of convection where hot mantle rocks rise and cold dense oceanic lithosphere sinks. So here we have rising hot mantle and we have subduction or sinking of cold lithospheric plate. This is the ultimate driver of the plate tectonics. Many of the details of this convective flow, however, remain the topic of debate in the scientific community. So here we can see in brief the different forces which operates the plate tectonics. So it is a ridge push where it occurs along the divergent plate margins, and the slab pull, it occurs along the convection plate margins. The gravity facilitates this movement. Slab pull and ridge push, let's explain this. So geologists generally agree that subduction of cold, dense slab of oceanic lithosphere is a major deriving force of plate motion, as we can see in this figure. This phenomenon is called slab pull. It occurs because cold slabs of oceanic lithosphere are more dense than one underlying the warm asthenosphere and hence sink like a rock, meaning that they are pulled down into the mantle by gravity. So lithospheric slabs, we can see over here, these slabs are subducting into the mantle because they are roughly 2% denser than underlying asthenosphere. Another important force is ridge push, as we can see in this diagram. This ridge push occurs along the mid-oceanic ridges. This gravity-driven mechanism results from the elevated positions of oceanic ridge, which causes slabs of lithosphere to slide down the flanks of the ridge. Ridge push appears to contribute far less to the plate motion than slab pull. The primary evidence for this that the fastest moving plates, the Pacific, Nazca and Cocos plates, have extensive subduction zones along their plate margins. By contrast, the spreading rates in North Atlantic Basin, which is nearly developed, or it is divide of subduction zone, is one of the lowest at about 2.5 centimeter per year. We can see along the Western Pacific, so that movement is facilitated by Eastern Pacific rise that has got the fastest spreading rate because it is associated with one of the fastest subducting plate. So this slab pull facilitates the movement of the plates, but in contrast with we see the North Atlantic, there we see that because it is divide of any subduction zone, proper subduction zone, so spreading rate is only 2.5 centimeters per year. Although the subduction of cold dense lithospheric plates appear to be dominant force acting on the plates, other factors also are at work. The flow in the mantle, perhaps described as mantle drag, is also thought to affect the plate motion, because if there are two things which are moving past each other, for example, this represents this hand represents the mantle and this hand overriding one represents the lithosphere. So if the convective currents into the mantle, they are moving in the same direction as the plate is moving, this is going to facilitate the plate movement, and if both are moving in opposite direction, that is going to resist the plate movement. When the flow in the asthenosphere is moving at a velocity that exceeds the plate, mantle drag enhances the plate motion. However, if the asthenosphere is moving more slowly than the plate, if the plate is moving and asthenosphere is also moving but it is moving slowly, or if it is moving in opposite direction, this force tends to resist the plate motion. Another type of resistance to the plate motion occurs along some subduction zone where the friction between the overriding plate and the descending slab generates significant earthquake activity. Models of plate mantle convection. Although the convection in the mantle has yet to be fully understood, researchers generally agree on the following mechanisms or following models. So in the first model they discuss there is convective flow in the rocky 2900 kilometer thick mantle in which warm buoyant rock rise and cooler denser material sinks. It is underlying the deriving force for the plate movement. The mantle convection and plate tectonics are part of the same system. Subducting oceanic plates derive and cold downward moving portion of convective flow, while shallow upwelling of hard rock along the oceanic ridge and buoyant mantle plumes are the upward flowing arms of the convecting mechanism. The convective flow in the mantle is major mechanism for transporting heat away from the Earth's interior to the surface, where it is eventually radiated into the space. What is known with certainty is exact structure of this flow. Several models have been proposed for plate mantle convection, and now we are going to look two of them, that is whole mantle convection and layer cake model. Now let's study the first convection model, that is whole mantle convection model. So there are group of researchers which favor some type of whole mantle convection model. It is also called as plume model, in which the cold oceanic lithosphere sinks to the greater depths and stirs the entire mantle. The whole mantle model suggests that the ultimate burial ground for these subducting lithospheric slab is core mantle boundary near to the D double prime layer. It is also known as slab graveyard. The downward flow of these subducting slab is generally balanced by buoyantly rising mantle plumes that transport hot mantle rock towards the surface. Two kinds of plume has been proposed, the narrow tube-like plumes and giant wellings, often referred as mega plumes, that we are going to study in some next classes about the mantle plumes. So there we will be studying about these type of plumes, the narrow plumes and the mega plumes. The long narrow plumes are thought to originate from core mantle boundary and produce hotspot volcanism of the type associated with the Hawaiian Island, Iceland and Yellowstone. Associated with India, we have certain mantle plume activities like the eruption of the continental flood basalt in Deccan Traps that is associated with one of the mantle plume activity. The scientists believe that areas of large megaplumes occur beneath the Pacific Basin and South Africa. The latter structure is thought to explain why South Africa has an elevation much higher than would be predicted for a stable continental landmass. So generally people consider that South Africa has got anomalous height, but this anomalous relief of South Africa depends on the occurrence of superplumes below the African continent. In the whole mantle convection model, heat from both type of plumes is brought or thought to arise mainly from the Earth's core, while the deep mantle provides a source of chemically distinct magmas. However, some researchers have questioned that idea, that instead proposed that source of magma is most hot spot volcanism is found in upper mantle asthenosphere. So there are two school of thoughts in mantle source, or we can say the mantle plume source. One school of thoughts proposes that source of the magma for the mantle plume is rather the core mantle boundary, and another school of thought proposes that source for the mantle plume magma is upper mantle. The second mantle convection model is layer cake model. There are some researchers, they argue that the mantle resembles like a layer cake divided at a depth of perhaps 660 km. So that is also a 660 km discontinuity, but no deeper than 1000 kilometers, as we can see in this diagram. The layer model has two zones of convection, a thin dynamic layer in upper mantle and thick larger sluggish located below the upper mantle. As with the whole mental model, the downward convective flow is driven by the subduction of cold, dense oceanic lithosphere. However, rather than reach the lower mantle, these subducting slabs penetrate to the depth of no more than 1000 kilometers. Notice that the upper layer in the layer cake model is littered with a recycled oceanic lithosphere of various ages. The melting of these fragments is thought to be the source of magma for some of the volcanism that occurs away from the plate boundaries, such as hotspot volcanism, for example in Hawaii. In contrast to the active upper mantle, the lower mantle is sluggish and do not provide material to support volcanism at surface. Very slow convection within this layer likely carries heat upward, but very little mixing between these two layers is thought to occur. Geologists continue to debate the nature of convective flow in mantle as they investigate the possibilities, perhaps a hypothesis that combines features from layer cake model and the whole mantle convection model.
These are the references utilized in the preparation of this class. Thank you. Jai Hind.